All right, let's talk about something we all just expect to work, flipping a switch and the lights coming on. Today, we're going to peek behind the curtain and get into the incredible, high-stakes balancing act that makes that simple thing possible. Let's get right into it.
So, here's the puzzle we're facing. Our power grid is getting more and more juice from solar and wind. That's great, but it's also unpredictable. The sun goes behind a cloud, the wind dies down. It means the demand on our big, traditional power plants is all over the place. It's a total roller coaster. So how on earth does a giant, slow-moving thermal plant react on a dime to keep everything stable?
To get our heads around this, you got to meet the two stars of the show inside that power plant, the boiler and the turbine. Think of them as the plant's power couple. How they work together, or don't, is at the heart of everything.
Okay, so here's the basic playbook, the four-step dance to make electricity. First, combustion. You've got fuel, air, and water getting pumped into the boiler. That creates a whole lot of high-pressure steam. Next, that powerful steam gets blasted at the turbine, making it spin like crazy. That's your mechanical energy. And finally, that spinning turbine is hooked up to a generator, and voila, you've got electrical energy.
You know, the best way to think about this is like a restaurant. The turbine, that's your super fast waiter. It's connected right to the customer, the grid. And when an order comes in for more power, bam, it responds instantly. The boiler, though, is the incredible chef back in the kitchen. It makes all the delicious energy, but it takes time to heat up the ovens and actually cook the meal. And that time lag, that delay between the waiter and the chef, is the exact problem we need to solve.
So, faced with this problem, what did engineers do first? Well, the early attempts were pretty straightforward. It all came down to one simple question. Who's the boss? Who's going to lead and who's going to follow?
So, option one is what we call boiler follow mode. In this world, the waiter, our turbine, calls all the shots. The grid screams for more power and the turbine immediately opens up to deliver it. This makes the steam pressure drop, which is basically the waiter shouting back to the kitchen, "Hey, I need more food." Then the chef, the boiler, has to scramble to catch up. It's super responsive, but you can imagine it's really, really tough on the chef.
Okay, so what's the flip side? That's turbine follow mode. And you guessed it, now the chef, the boiler, is in charge. It cooks at a nice, steady, comfortable pace. And the waiter, the turbine, is only allowed to serve what's actually ready. It's way more stable and safe for the kitchen. But the downside? It's incredibly slow to respond if a big party suddenly walks in the door.
So you can see the dilemma here, right? On one hand, boiler follow gives you that lightning-fast response the grid is demanding. It's all about megawatts right now. On the other hand, turbine follow gives you that slow, steady, stable operation that keeps the machinery happy and safe. It's this classic engineering puzzle. Do you want it fast or do you want it safe?
And this table just lays it all out, plain and simple. Boiler follow? Yeah, it's quick, but you're playing with fire with those massive swings in pressure and temperature. That's risky. Turbine follow? Rock solid, super stable, but just way too slow for what the grid needs today. Clearly, neither of these is the perfect answer.
Now don't worry about all the squiggly lines on this chart. The only thing you need to see is this. When demand changes, the turbine's power, that's its response, shoots right up, almost instantly. But look at the boiler's fuel. It takes its sweet time catching up. That gap you see right there, that's the time lag, the fundamental problem we've been talking about.
So, okay, having one just follow the other, that's not going to cut it. Engineers needed a better way, a smarter approach. They thought, hey, what if instead of following, they worked together, as a team? And that is exactly where coordinated control comes into the picture. This is coordinated control mode, or CCS for short. And for a long, long time, this was the absolute gold standard. Think of it like a really good restaurant manager. The manager gets the order from the customer, that's the grid, and instead of just telling the waiter, they run to the waiter and the chef at the exact same time with the same instruction.
And you can see that idea right here on this diagram. See this main signal coming in? That's the demand from the grid, the order. And look, it splits. One command goes straight to the turbine, the other goes straight to the boiler. They both get the memo at the exact same moment. It's not a game of follow the leader anymore. This is a perfectly choreographed dance.
And the results? Oh, they're huge. Suddenly, the boiler and turbine aren't fighting each other anymore. You get this beautiful balance between meeting the power demand and keeping the plant stable. And get this, it's smart enough to use the steam that's already sitting in the pipes for a quick burst of energy during a sudden spike. It's just a much more elegant and efficient way of doing things.
So for decades, everyone was happy. Coordinated control was the king. Problem solved, right? Well, not quite, because the game changed. All of a sudden, you've got all this renewable energy on the grid, causing these wilder, faster, more unpredictable swings. And now, even this advanced, coordinated system is starting to sweat.
And that brings us right to the edge of what's happening today. Is this great system great enough anymore? Is being a good team player still enough when the grid is demanding a response not in minutes, but in seconds or even fractions of a second?
And the research is telling us, probably not. This quote here really nails it. What it's basically saying is, at the end of the day, you're still dealing with huge physical machines. Valves have tiny delays, moving parts have a bit of stickiness to them, and when you add up all those tiny little imperfections, the whole system just can't physically move fast enough anymore. So this new challenge forced engineers to come up with something completely different. It's a whole new philosophy called direct energy balance, or DEB, and the core idea here is pretty radical. Instead of just coordinating the boiler and turbine, it changes the logic entirely. It looks at the total energy in the whole system, including the steam that's already stored, and it makes a single holistic calculation to get a near-instant response.
Now, we're not going to get lost in the weeds on this diagram, but it gives you a taste of how different DEB is. It actually bypasses some of the traditional slower control steps and acts directly on the plant's total energy balance. This whole thing is designed for one thing and one thing only: pure, unadulterated speed. So just look at how far we've come. We started with a simple game of follow the leader, then we moved to a synchronized team, and now we're talking about a system that thinks in terms of pure energy. The big question is no longer just how to coordinate, but how to predict and control the total energy of a massive power plant in real time. So how does DEB actually pull off this magic trick? Well, that's a deep dive we're saving for our next explainer.